3, 2, 1.
Alright, welcome to section 3.2. I wanted to show you that pretty extreme clip of the Hot Wheels real life example there, because we're going to be talking about extreme points on our graph today. Okay, so extreme points meaning like the highest or the lowest points. Little disclaimer about that Hot Wheels clip. Okay, please do not try that on your own. I don't want anybody getting hurt, but I still think it's pretty cool just to see what people can actually do when they put their mind to something. Okay, so that was pretty awesome. So I'm getting into extrema and function analysis. Extrema are those extreme points that we're going to be talking about today. And our first classification, I guess you could say, of extreme points are either the absolute max or the absolute min. So these absolute maximum or minimum are absolutely the highest or lowest points on your graph. So if we take a look at our graph right here, we want to find either the highest and or the lowest points on our graph. And if you take a look at your graph, it looks like the highest point is somewhere right there. So we would label this as an absolute maximum. Okay, it's the highest point our graph actually goes. Now, if we think about the absolute lowest point, we don't really have one in this case, because notice how the arrows are going to go completely down forever and ever and ever. They're never going to end. So we really don't have an absolute lowest point, because these are just going to continue on forever. So in this case, we only have an absolute max, but sometimes, depending on the graph that you're looking at, you could have an absolute min if it's the absolute lowest point on your graph. Now, if you notice on your graph, we kind of have some other high points like this one right here, and we also have a low point right here, it looks like, but they are not the absolute highest or lowest. These are what we would call relative local or relative maxes and mins. So these relative ones are more points on our graph or our picture here that are high points or low points, but they're higher or lower than all the points immediately around it. So if we just take a look at this little section right here, we're just looking at the graph kind of around this point. Notice how this is the lowest point when we look at the graph completely around it. We almost have this directional change where we go from decreasing to increasing. So that directional change is giving us a low point. We would label this one as a relative minimum. Okay, it's not the absolute lowest point, but it is another low point on our graph. Now, same thing going on here. If we just take a little section of it and take a look at it, notice how we have another directional change. We go from increasing on our graph to decreasing, which is giving us that high point. And since this isn't the absolute highest or the absolute max like we classified this one, this would be considered a relative max. So I think they're kind of easy to remember the difference. The absolute max and min are the highest or the lowest because they're absolutely the highest or lowest, but the relative ones are just other high or low points you might have on your graph. Now, when we go through the other examples in the lesson today, we're going to be talking about finding a max or min, which means finding the y value of the point. Okay, so the x value here helps you with the location, so we can say, in this case, the absolute max happens around -2, but when we're talking about the actual value, okay, finding the value of that absolute max, we would say the value of it is about 3. So the x value gives the location, but the y value gives you the actual, I guess, value of that maximum or minimum. Alright, so taking a look at our first example, we want to find the coordinate points of the extrema. Okay, extrema meaning those extreme points, and we want to classify the different types. So we want to find all those absolute maxes and mins if our graph has them, and we want to find those relative maxes and mins if our graph has them. So this is a pretty ugly function here, and I kind of give you a general picture of what it looks like. So just to maybe label the points that we want to look for, it looks like we have an absolute min right there, the lowest point our graph has. But we have a relative min right here. Notice how it's not the lowest point, but it's another low point on our graph. This point right here we would consider a relative max because it is a high point, but it's not the highest because if you take a look at the arrows, the graph is going to continue up and up and up forever and never going to stop. So since our graph does not have an absolute max, this would be considered a relative max. Now, I know based on the picture we can kind of guess about where these points might be. It looks like the absolute min might be somewhere around 4, -60, but we're going to try to be as accurate as possible because if you take a look at it, that absolute max actually doesn't happen at that 4, -60 coordinate point. Okay, it's pretty close to it, but it's not quite that value or that coordinate point. So in order to be as specific as we possibly can, we're going to use a graphing calculator to help us out. So if we want to graph this, you need to go to your y equals button, and I already typed it in here just to save us some time, but I think you guys can go ahead and type that in on your own. And we want to hit the graph button, but before we do that, let's automatically change our window. Okay, so my window is pretty messed up right now, but based on this graph right here, we can actually pre-program our window based on what we have here. Notice how on our x-axis, it looks like our lowest value we could say is a -5, and our highest value, since we're counting by 2's, looks like an 8. Now if we go off of our y-axis, the lowest value maybe we'll say is -70, and our highest value, since we're counting by 10's, looks like 30. So based off of this graph, since we clearly see a really good picture of what our graph should look like, let's program our window to match this window. So our lowest x value we want is -5. We want our highest x value to be 8. And they're counting by 2's, so I'm going to count by 2's just to match them. The lowest y value looks like -70. And the highest y value we want to go to is 30, and they're counting by 10's, so I'll count by 10's as well. So now if we hit graph, our calculator should look very similar to what we have already here. And it's very slow because it's a very complicated equation, a bunch of decimals, a bunch of terms, but it's just going to take its jolly old time. And whenever you see this little like cursor thing moving here, that just means it's thinking. Okay, it's graphing it or thinking about it for you. And it's done. Okay, so notice how our picture looks very similar to what we have here. So let's just label or classify the different types first, and I'm going to show you how you can use your calculator to find those specific values. So it looks like we had an absolute min, so maybe we'll write that first, absolute min. Then we had a relative min. Okay, I'm abbreviating just to save space, but you guys can write out the actual words. And it looks like we had a relative max as well. So those are the only 3 extrema points that we have. Okay, everything else, we don't really have an absolute max, or we really don't have an absolute max, so we don't have to worry about that. So let's focus on finding this absolute min first. We can anticipate something close to 4, -60 because it looks really close. Alright, so on your calculator, we can go to second calc. Okay, remember we went to that option when we used that 0 when we're finding those x-intercepts. But today we're going to talk about using the minimum and maximum values, or those 3 and 4 options. So since we're specifically looking for a minimum, okay, in this case the absolute minimum, we want to select option 3 because that's what we're trying to find. Now, just like when you use the 0 option on your calculator, it's going to ask you to pick a left bound. So if this is where we think the absolute minimum is, we want to pick a point somewhere on the left-hand side. So you can use your little cursor here to help you with that. So this is the point we're guessing. We want to pick a point on the left-hand side to give the calculator a left bound. So it's going to give you that arrow saying that the calculator is going to focus right of this point. But now it's asking you for a right-hand bound. So we're going to pick a point on the right, maybe right there. And there's another little arrow that pops up. So that's telling your calculator to only look for that minimum value between those 2 arrows. And last but not least, it's going to ask you to take a guess where you think it is. So maybe we'll say about right there. And if we hit enter, It's thinking, but it's going to give us a minimum value of 4.168, and then negative 57 point, we'll say 67, we'll round it. So notice how it was really close to that 4, negative 60, but this is the actual absolute minimum of our graph. So let's write that down. We had 4.168, negative 57.67 if we round. Alright, now we're going to do the same thing, but maybe we'll take a look at the other minimum value. We'll go to this point on our graph. So we're going to take a look at this one. Again, it's a minimum that we're searching for. So when we go to that second calc option, we're going to select number 3. And we're going to repeat the process. So it's going to ask you for a left-hand bound, but since this is the point we're focusing on, we want to go somewhere left of that point. And I guess my cursor is pretty slow. Alright, bear with me. Alright, somewhere left of our point, maybe we'll say right there. Now it's going to ask you for a right-hand bound, so let's go somewhere on the right-hand side of that relative minimum. Maybe right there. And again, it's going to ask you for a guess. So where do you think that minimum is? Maybe right there. And we have, if it's going to think for us, a minimum at negative, we'll say 2.583, negative 41.337. Okay, so that's our relative min. Negative 2.583 and negative 41.337. There we go. So if you notice, kind of close, okay, a little bit smaller than negative 2 and a little bit lower than negative 40, so that's making sense. Last but not least, let's find our relative max. So that's the point in the middle. Now this time when we go to second calc, since we're focusing on a maximum, we want to use option number 4 and repeat the process. If this is the point we're searching for, it's going to ask us to pick a left point. So maybe we'll select that one. And now we want to go on the right hand side. It's like we're trapping it. We're telling our calculator to focus in between these 2 points. Okay, so somewhere in between these 2 arrows. And lastly, just to give our calculator kind of a head start, we're going to give it a guess. Maybe right there. And while it's thinking... Oh, okay, this one's really interesting. Notice how it's 1.6505e to the negative 7. Okay, that e is telling us scientific notation. So we want to move this decimal place 7 places to the left. Okay, that negative means to the left. So if we were to move this 7 places to the left, it would be 0.00000016505, which is practically 0. Okay, very, very, very close to 0. And our y value is 1. So we'll say our relative max is practically 0, 1. Now this is where a calculator is or that option on your calculator is really nice, because if you were to just take a look at this picture, it almost looks like the relative max is at the origin. Okay, it kind of looks like it's at 0, 0, but it's actually not. Okay, it's really close, but it's actually at 0, 1. So looking at a picture might be a little bit vague. You can get close to the actual value, but when we are able to have an equation and we can type it into our calculator, we can find the actual values or coordinate points of those extrema. Alright, so using your calculator is a really, really helpful tool for finding that information. Now if we look at the last one, it says what is the minimum value. So if we're trying to find a value, we're looking for the y value of our ordered pair. Now if it's asking for the minimum, okay, that means it's like asking for the absolute minimum, the lowest point on our graph. So if we take a look at our absolute minimum, the y value is negative 57.67. Okay, that is the lowest possible value or point on your graph. So that would be the minimum I'm stuttering today, minimum value of your function. Alright, so I want to take a second and just discuss with you the difference between having these closed points, these open points, and even a jump discontinuity when it comes to identifying those extrema. Okay, do we have an absolute max or min or a relative max or min? So if we take a look at this point right here, notice how it's kind of just by itself. We don't really have a graph extending from the other side. And we know it's not the absolute max because clearly the left-hand side is going to go up forever. But it might be a relative, because remember the definition of a relative max or min is that it's higher or lower than all of the points immediately around it. So if we just take a look at the area around that point, notice how this one right here is the highest because the other points immediately around it are lower than this value. So we would be able to classify this as a relative max. Okay, because it is the highest point just immediately around some of the other points. Clearly right here, okay, maybe we'll label that as an absolute min, because that is the lowest our point goes, okay, right there. But this end point right here we would consider a relative max because it's higher than the points around it, but it's not the absolute highest. Now the difference over here when we have an open endpoint, hopefully we know that when we have an open circle, that means there's no point actually there. Okay, so if there's no point, that means there's no value to it. So this point actually means nothing. Okay, nothing, nothing, nothing. There's absolutely nothing there. I think someone in class actually referred to this point as a ghost, okay, because there's nothing there. It's completely empty. It's almost see-through, I guess you could say. So this point, different than this one, is not considered an extreme value because there's no point that's actually there. We still have that absolute min, just like we had over here, because it's basically the same graph, but this point would not be considered anything because there's actually no point there. Now when it comes to a jump discontinuity, notice how we still have a point right here, but now that we have this other piece, okay, this other piece is going to continue forever and ever and ever down, meaning that this point is no longer the absolute min, it actually turned in to a relative min. So just by adding another section of your graph, because this piece didn't show up in the other ones, you can change the classification of your extrema. Okay, points can go from being absolutes to relatives just based on the other pieces of your graph. So in this particular graph, it would be considered a relative min. Again, this point is considered nothing because there's actually no value there. But this point up here, notice how it's not the absolute max because this end of our graph is going to go up forever. But if we just take a look at the points immediately around it, this closed circle is higher than all of the other points around it because these are clearly smaller or lower than that value. So this point would be considered a relative max because it is a high point, but it's not the highest because this end of our graph is going to go up forever. So you really got to be careful. Do you have a closed dot? Do you have an open dot? You got to look at your graph as a whole to figure out how far up is it going, how far down is it going. Are you dealing with absolute maxes and mins, or are you dealing with these relative maxes and mins? Alright, so let's just talk about for a second about finding a friendly window on your calculator. Some of us are still having a little bit of trouble with this because I know you guys like to use that zoom fit option just to get a general picture, and then you guys experiment a little bit to find a window. But I'm going to show you kind of a quick and shortcut way to doing that, or to find a friendly window just by looking at your equation. So if we go ahead and type this into your calculator, you can go ahead and do that. But one particular number on here that's pretty important is the last number in your equation, at least when you have a, sorry about that, when you have a cubic function, because we have a power of 3, or even a quadratic function if you just have a power of 2, the last number is always your y-intercept. So you know that this point is going to be on your graph. So specifically in this example, we're going to have a y-intercept of 0, 5,000. So that's telling us a really good value about what our y-min and y-max should be because we know this point is on our graph. Now we might have to experiment a little bit with our y values, but this point is giving us a good look about where our y min and y max should actually go. So if we were to type it into our calculator, I think I already did that for us. Let's just go to our window for a second, and right now I have a standard window, but I'm going to only change my y values to fit this particular idea. Okay, so I know that my graph at least has to go up to 5,000. So maybe my max, I'll say, is 5,500. I'm just going to guess. Okay, but I know my graph should go, my graph should at least go up there. And, okay, going from -10 to 5,500 is a pretty big jump, so maybe I'll make that jump just a little bit shorter for us. Maybe I'll start at 4,000. Okay, again, I'm experimenting, but I'm using an educated guess about where these numbers should be based on this y-intercept. So for now, I'm just going to change the y values, and I'm going to hit graph just to see what I have so far. And it's going to think for us, so just give it a second. And that looks pretty good. Okay, so notice how a cubic function is going to look either like this, or if we flip it, make it negative, it's going to look like this. And since it's negative, this is the graph that we're focusing on. And that's what this picture actually looks like. But notice how I have all this empty space to the left, and I have all this empty space to the right. So I can go ahead and go back to my window and change my my x values. I don't need to go all the way to -10. Maybe I'll just go to -5. And I don't need to go all the way to 10. I can be shorter than that. Maybe I'll just go to +5. Alright, now down here my y scale was pretty dark, and counting by ones is going to be a lot of tick marks. So maybe I'll just go by 500s. Okay, so notice how we can clearly see our tick marks on the y-axis. I'm only going to -5 over here, I'm only going to +5 over here, and my graph looks much nicer to us. So clearly, since we know it's a cubic, this end is just going to continue going up, this end's going to continue going down. So I'd say that's a friendly window for us. You just got to be careful, because let's say there was a question that was asking for the 0 or the x-intercept of your graph. Okay, that's where you got to know that an x-intercept occurs when your y value is 0. So this particular window would not work for that, because our y value only goes down to 4,000. Okay, we want to see our x-axis in that particular example. So I would have to go negative, I don't know, maybe I'll go -100 or 1,000. Okay, we'll try that. And now notice how we can see that x-axis. Okay, so you got to be careful, because depending on what the question's asking you, you want to make sure you can see what you're trying to focus on your graphing calculator. So if we wanted to find the x-intercept, you got to change your window, which would give us that point right here. So depending on what you're trying to find, you can change your window. But I would say a friendly window would be the original one, because we were able to see the general shape of the graph. Okay, we were able to see this negative cubic picture. So maybe we'll say our x-min was -5, our x-max was 5, we counted by ones. The lowest y value we had was 4,000, the highest was 5,500, and we counted by 500. Alright, so last but not least, we have function analysis, which is basically putting everything all together to help us analyze this function. So we're going to be doing everything from Unit 2 and everything that we've been talking about so far in Unit 3 all together with just one function. So the first thing we want to do is find the domain, and algebraically from the last lesson, that means looking for a fraction and also looking for a square root. And in this case, we have both of those going on. So in a fraction, we know our denominator cannot equal 0. So some domain values or x values that are not going to work in this particular function would be that x cannot equal 2. Okay, if we were to actually separate these factors and solve, x would not equal 2 from this example, and x would not equal -3 from this example. But we also had a square root, which means it has to be greater than or equal to 0. So if we do that, x minus 1 is greater than or equal to 0. We have some x values that work, but they have to be greater than or equal to 1 based on our square root here. So if we put everything together, okay, our final domain would be x values greater than or equal to 1, but x cannot equal 2 or -3. Okay, so that would be our final domain. So now let's move on to some vertical asymptotes. So we want to take a look at our equation, and remember the vertical asymptotes are those non-removable discontinuities, whereas the holes over here are the removable ones. So based on our function, can we remove any factors, or are there things that are kind of left over? They were not able to be removed. So if you take a look here, we have an x plus 3 factor in our numerator, which is going to cancel out with an x plus 3 factor in our denominator, so we can remove those, which means that this discontinuity at -3 would be a hole. So we should have a hole at the x value of -3. But notice how we're actually left over with a square root of x minus 1 up top, and our factor of x, that actually looks like a 4. Let me try to get rid of that. We have the square root of x minus 1, and in the denominator we have our factor of x minus 2. So we still have this factor in the denominator. Okay, this x value of 2 is still not going to work, so we would have a vertical asymptote at the value of 2 for x. Alright, now for the other ones, this is when a graph is going to help us out because we can find maxes and minimums graphically. We can also find those increasing and decreasing intervals, and we can also talk about a horizontal asymptote, or that end behavior. What's going on as our graph moves all the way to the left, and what's going on as our graph moves all the way to the right. So let's go ahead and take a sketch of our graph, and we can use a calculator to help us out with that. Again, just be careful, since we're dealing with a fraction overall, we want to put the entire top in parentheses and divide it by the entire bottom. So we gotta be careful when we use our calculator. So we're gonna have a double parenthesis, and we'll have x plus 3. Okay, notice how I'm using the original function, not the reduced one, because this is what we originally started with. And we have the square root of x minus 1. We can close that parenthesis, and we're going to divide the entire bottom, which has two factors. One is x minus 2, and the other factor is x plus 3. Again, we need that double parenthesis to close it off. Now, strategically speaking here, we can take a look at our graph to help us with our window. It looks like we go from negative, is it 5? 1, 2, 3. Yep, -5 to +5 on our x-axis. And it looks like I'm already doing that. And we're counting by ones. But we're definitely not going into the thousands like we were in the last example. So this would be -5 to +5. Let's change that. And we are going to count by ones as well. So let's hit graph and see what happens. And there we go. Alright, so we said we should have a vertical asymptote when x is 2, and it looks like we have that right here. So maybe on our graph when x is 2, we'll draw that vertical dotted line, that asymptote. And it also said we should have a hole at -3, which is somewhere over here, but we do not actually have a graph over here. So let's go back and discuss about what's going on here with our domain. Notice how the only x values we said would work were x values that were greater than or equal to 1. And clearly that's going on here, because notice how my graph starts when we have an x value of 1, and it continues to the right, meaning all the numbers greater than that. So this -3, since it's actually to the left of our starting value, because our starting value is 1, we don't really have any graph going on over here. So we don't really have to worry about labeling that hole, because this is kind of the starting value. When we have x is greater than or equal to 1, that's the beginning value of our graph. So we don't have to worry about the left-hand side because this is our starting point. So if we continue to kind of draw this, it looks like it begins at 1 and continues down. So we'll do that. And then over here, it kind of does the curve shape, but notice how it's starting to level off when it approaches this x-axis. So we will level off at the x-axis like that. Okay, so there's our graph. Now let's talk about the maximums or minimums, and we want to discuss the type. So this is going to continue all the way up, which means we don't have an absolute max. This piece is going to continue all the way down, so we don't have an absolute minimum. Okay, so we don't have to worry about those, which means we might have some relative points. Now, this point right here, okay, notice how it's a closed dot, so we actually have a point there. And according to the definition of relative, we just want to look at the points around it, and this would be considered a relative max because the other points around it are lower. So we would have, we can say here, a relative max, and that particular point right there would be 1, 0. Alright, now minimums, we said we had an absolute, or we did not have an absolute minimum because it's going to continue all the way down. And some of us might be confused about this point right here, but notice how it's not a minimum because this point, or this graph, at least at this spot, is going to continue decreasing. So we don't really have a minimum at all. So we'll just say none. So now let's talk about the increasing and decreasing intervals. Remember, we want to think about our little ladybug as it travels through our graph. What is it doing? So if it starts right here at the dot and travels, it's going to continue downward. So that particular point where it starts is 1. And as it decreases, it's going to decrease until it gets to this x value of 2, because that's where our asymptote is. But we still have another section of our graph, so as our ladybug kind of jumps or moves over that vertical asymptote, it's going to start somewhere up here, but it's also going to continue to walk forever down our graph. So it's actually another decreasing interval from 2, remember it started on the other side of 2, and it's going to continue decreasing all the way out towards infinity for that x value, so that would be when it ends. So we really didn't have an increasing interval. Our little ladybug was decreasing the entire time. Now, talking about the left and right hand side and behavior, this is when we're talking about those limits. So we want to figure out as x goes to -infinity from our function, what is happening, or for that horizontal asymptote, because we already found that vertical one. We want to try to figure out where is our horizontal one if we have one. And then the right-hand side, we would be going to positive infinity of f of x of our function. So we check this out. As we continue on our graph going all the way to the left, okay, we don't really have any piece of our graph over here on the left-hand side. So if our x value cannot approach -infinity, okay, it's never ever going to be going off to the left-hand side, the limit does not exist. Okay, so we're not really approaching anything as we continue off to -infinity because our graph does not go all the way that direction. But notice how if we move across our graph to the right-hand side towards positive infinity, our graph is approaching the x-axis, meaning that has a y value of 0. So our horizontal asymptote, this right end behavior in this case, would be approaching 0 as we go off to positive infinity. So that's a lot of stuff to take in right there. Notice how we're combining everything we've talked about from Unit 2 and so far in Unit 3 in one problem. These can be a little bit overwhelming because there are a lot of different pieces that are going on, but I always recommend using your graphing calculator to help you out, especially when you sketch a graph or you can look at a graph. It's going to help you analyze these different pieces. So good luck on the practice, good luck on that application, and good luck on the mastery check.